Hello, I'm Anirudh, and I will be presenting this paper called Orchestra. It's about a lightweight hierarchical orchestration framework for edge computing. To set some context, edge computing is computing that need not necessarily be on the Internet of Things, but in general is located much closer to your user than any sort of regular computing, right? So for example, if I have my application deployed in the US, right, and I'm in India, there is a non-negligible amount of latency that it takes for data to get from the US to India. Edge computing aims to solve some of that by, in general, bringing data closer to the user. So this can mean having data present in India itself, as opposed to me having to do a full round trip to the US via a bunch of subsea cables or via satellite or whatever. To make my experience better. This obviously brings with itself a host of new challenges about, especially from a distributed systems point of view, about how you do things like maintaining consistency when you have these non-negligible, non-data center sort of bounds or challenges, constraints within your infrastructure. Orchestra is basically supposed to be Kubernetes, but for the edge. And before we go a little deeper, this is me. I'm a computer science senior at PES University from India. I love systems, distributed systems, databases. I worked at this company called Bäurle before, working on MQTT brokers. I'm currently still in university. Ways to get in touch with me. I really like poetry. So if you like poetry, that's a plus. Getting to it. So let's start by understanding why this is a problem. And the slides, I apologize, are a tiny bit more text heavy than I would like. But I hope the discussion will make up for it. So let's get started. So why is this a problem, right? Edge, while it need not necessarily mean IoT, does imply a lot of heterogeneity in terms of your devices. So edge computing can mean that you have a bunch of network constraints, which means that your devices need not be in the same data center, same continent, same planet, right? So there are these constraints that you have to keep in mind. They're also not homogeneous in terms of compute capacity. So it can be an Intel, so it can be an NVIDIA Jetson, it can be an NUC, it can be a Raspberry Pi, it can be some bespoke sort of computing solution that someone else has whipped up. All of these fall under the gamut of edge devices, right? And obviously, when you have a massive fleet of edge devices, right? So let's say you're a company that runs smart farms, and you have a lot of these edge devices present that are constantly getting sensor data for you and are constantly pushing it back to whatever, OLAP aggregation sort of system or any sort of reporting system that you have. You need some way to orchestrate over these systems. So can I just get a quick show of hands, if that's possible, about how many people are familiar with Kubernetes? Okay. All right. No, absolutely no issue if not. To quickly explain that, Kubernetes basically just lets you place a container on a device to run an application. And the reason this is necessary is because you have a large number of devices and you have a large number of containers. Deciding which container to put on which device, how to connect them up via a network, is a pretty hard problem to solve manually. And we used to do it manually, but we don't anymore for the most part. So Kubernetes does that. Obviously, it's a lot harder to do with edge devices because there's a lot of constraints that you have to account for, right? Maybe this application doesn't run well on this particular type of device, so I need to find an alternate device. Maybe it's not possible for me to run this application on this type of device, right? These are all things that you have to take into account when you're looking at orchestration for the edge that Orchestra tries to solve. The thing is that Kubernetes doesn't really work well for the edge, right? And we'll talk more about why a little bit later on in the presentation. But Kubernetes does not really work well for the edge. And when I say it doesn't work well, I don't mean it doesn't work at all. I mean, it does work, but with a significant performance hit. And we'll explain why. The other thing is, as a part of the network constraints, a lot of your devices can usually be dropping in and out of connectivity. So let's say it's an EV that's moving between service zones, or even just a regular vehicle, right? That's moving in between connectivity zones that your cell towers might have. Obviously, there are regions of our countries that don't have cellular network connectivity or might not have satellite internet connectivity. So this is a problem that you might see. And the other last thing that's a problem is that it's very hard to talk to another edge device from one particular edge device, because if you do as much as try to set up a simple Raspberry Pi server at home, you'll see all the things that you have to do, right? You gotta talk to your ISP about getting a permanent IP, or you have to do some sort of NAT traversal. It's a mess, right? So this is a problem that is yet to be fully solved as far as I know. So what is the big idea of Orchestra? The big ideas are basically that you want to do orchestration for the edge without using Kubernetes. And how do you do that? The reason Kubernetes doesn't work, which we'll get to later, but you'll have to trust me for the next 2 slides or so that these things sort of solve that problem, right? The big idea that Orchestra proposes is that instead of having the way you do in Kubernetes, instead of having one control plane and multiple worker nodes, right? You would much rather have one global scheduler or a global orchestrator, and you have clusters sort of signing up to federate into this network of clusters that you have. So you delegate very fine-grained scheduling decisions to your local clusters. Why this works, or what the benefit of this is that your central orchestrator does not have to take as many decisions. As far as I know, deciding the optimal fit for a service on a cluster is a really hard problem to solve. I'm not exactly sure about which class of computational complexity it falls into, but as far as I know, it's a pretty hard problem to solve, right? So you take off some of the load of the central orchestrator by delegating it to a local orchestrator. Yeah, someone has a question. I think that's Michael. I don't think I can see the chat. So
sorry, I left my hand up from when you had asked about Kubernetes experience.
Okay, cool. No, sure. So yeah, and this will make a lot more sense when I get to the architecture diagram. But you're essentially trying to reduce load for fine-grained scheduling decisions from the global orchestrator by having a bunch of clusters of local, by having a bunch of clusters sign up to be a part of this network. And the second big idea that I found, at least, is that they use an overlay network for inter-service communication. And they do this by having each node or each worker node have its own networking manager, the same pattern you would see in something like a sidecar proxy, right? So something similar. And they mention it in the paper too, but something similar. And the other cool part is that they have semantic routing. So as you'll see later, I can basically do, if I want to hit the nearest instance of a particular application, right, in the domain name of that application itself, through Orchestra, I can say nearest dot this application slash API slash v1 slash and so on. And the overlay network will take care of that routing for me. So I don't have to set up additional equipment to do that. The overlay network takes care of that for me. Are we doing okay so far? Any feedback, any suggestions so far? I can't see chat, so it's a bit difficult. If anyone has anything to ask, add on, please. Would love to hear that. Okay, I can see chat now. Cool. Awesome. So assuming nothing else, we'll move on. Just a quick display of results. They did manage to show that their framework does better than Kubernetes, MicroK8s, and K3s on a bunch of different benchmarks. They basically set up 2 types of applications. The first one was basically a simple collection of HTTP servers that they ran GET requests on. And the other one was a relatively complicated microservice setup that does facial recognition and object detection and object tracking and so on. So in general, what they've managed to do is they've managed to show that even running in a single cluster mode, right, which is one of the problems I have with this. But even running in a single cluster mode, they managed to show that they are a much more lightweight and more efficient version of Kubernetes and its derivatives. But I would take these results with a grain of salt, and we'll get to it. So we can see that it takes a lot lesser time to deploy. They managed to reduce resource utilization by a lot, which is a very valuable thing if you're deploying on the edge, because it directly translates into lower power consumption for you. They've also shown that deployment time is somewhat lesser with Orchestra as opposed to K3s. And I had a little bit of trouble deciphering this last diagram about end-to-end latency, so maybe we can discuss that a little bit later. But the headline of their result is that they've managed to get a roughly 10x resource usage reduction with a 10% improvement in the application performance. So again, if you have any questions, feel free to interrupt or drop it in chat and we'll get to it. But seeing none right now. You might be asking, right, why not Kubernetes? So one of the references in the paper mentions a paper by Andrew Jeffrey, Heidi Howard, and Richard Mortier, if I'm pronouncing that right, which basically talks about why Kubernetes doesn't work out for the edge, right? And lying at the center of this problem is etcd. So I assume, okay, so etcd is a distributed key value store, right? And the idea with etcd is that it's used as the backing store for all of Kubernetes. So any information that you put into Kubernetes or any request that you make to Kubernetes basically hits etcd in some way. And the black box overview of it is that etcd does not really scale for the edge. etcd runs on Raft, and Raft as a consensus protocol has a lot of latency constraints on exactly how slow the slowest request can be, right? For those of us who are not familiar with Raft, the way it works is that you have multiple nodes in a cluster. And actually, it's probably better if I visualize this. So just... So there's this really good Raft visualization called the Secret Lives of Data. It walks through exactly what's going on. So we can, great resource, please check it out, but we'll skip this for now. I'm just trying to get to the part where we talk about getting consensus with multiple nodes. And what I'm trying to demonstrate is that there is a leader election that happens in Raft that's based on a randomized timer. And if your timer runs out, any node will want to become a leader. And you don't want this happening too often, right? Raft has mechanisms to make sure that this doesn't happen way too often. But as you can see, there are randomized timeouts. And based on how long your request takes to come from point A to point B inside the Raft cluster, it can trigger a leader election again. So it's not impossible to get past this, but it is a significant perf hit, right? So Kubernetes relies on etcd, which relies on Raft, and etcd is a very hot path component of Kubernetes, which means it's hit a lot during each request. So because of etcd, basically it doesn't quite let you use Kubernetes on the edge with the same performance that you'd get if you used it in a data center, which is fair, right? Kubernetes wasn't built to be used on the edge. It was built to be used inside Google's data centers. So yeah, basically that. And Kubernetes also has a lot of really compute intensive operations. Like deciding which node to schedule which container on is a really compute intensive operation. So on systems that have much lower compute capability, it won't work as fast. So this is why Kubernetes is probably not the best solution for that. Coming to the architecture, I feel like I've been rambling for a bit. Does anyone have any questions? Okay, cool. See, oh, sorry, someone had a question.
I have a question. I just wasn't sure what the format is like with regards to questions, but one of the things that I find a little bit challenging to wrap my head around is this idea of So in edge computing, this theme of machines not being as compute intensive or having lots of resources seems to be key. And it's it's not really apparent why, for instance, I'm able to set up a availability zone that's closer to my users via something like AWS, right? And those are really big, powerful machines. So, like, why is it in this case that these machines must be of lower constraint, meaning they're not as resource intensive? I don't understand. Like, why is that? That seems to be the theme. There also seems to be a theme in the paper where they displayed images of edge computing devices as Raspberry Pis and Intel NUCs. So it's hard to kind of wrap my head around that.
Okay, so I assume you're done with your question.
Yep.
Okay, so here's an example use case that I worked on, right? So let's say you're running a smart file, or fine, we'll stick with like a hydroponics sort of setup that you've got running, right? In this sort of setup, it's very critical for you to have metrics on like your soil moisture content, your pH levels, your electrical conductivity levels for your water, and so on. Now you can have, let's say, 100 different individual sensor clusters, right? But from a cost point of view, it might not make sense for you to have each and every one of them connected to the internet, right? So a common approach would be to add a layer of indirection and say, hey, I'm going to have a local sort of NUC here, which is going to be responsible for communicating with these 100 devices and only these 100 devices, right? It's going to collect all the data from these devices. And that's the only machine that I've connected to the internet. So that's the machine that speaks to your, stream analytics service, whatever you've got running for your analytics. But you don't need to have all of those 100 devices connected to the internet itself. So when we say edge, it need not necessarily, you don't need something in AWS for this, right? You can do it a lot cheaper, with a lot less in terms of setup, I would say. And you in general have a lot more control over it, right? So this is a use case I would see as to why edge computing might refer to much smaller devices than something AWS would give you. But I'm happy to hear any other answers on this. Anyone?
A good example of the edge would be like cell towers, by the way. So you don't really like have a lot of room, a lot of power requirements and so on and so forth to support like too many big machines at the cell tower, right? But you will have some compute, some devices to that exist on this cell tower and do some of the edge computing stuff, for example, for the network provider.
Yep, I think that's right. Does that answer your question?
Yeah, I mean, to some extent, right? Because the paper also describes Orchestra as being this federated orchestrator in which ISPs and cloud providers can all run their own infrastructure, which just also complicates things, right? Because why would a cloud provider be providing me with maybe some machine that's a Raspberry Pi, right? Like, it's hard to wrap my heads around something like that.
No, I get where you're coming from, right? But I feel like the use case that these people are talking about when they talk about this sort of an edge deployment is that it need not necessarily be just a Raspberry Pi, but it can be one. I think that's what they're talking about when they talk about heterogeneity, right? Because it need not just be that you have only Raspberry Pis or only data center class compute being available to you. I think the federation model, there are different takes on this, but I feel like ultimately it does make sense because you get to, and you have two-level scheduling, delegated scheduling here that we'll get to. But I feel like it does make sense because it's a lucrative business model to some extent. Like you can just, let people, you buy the hardware, people take care of running it and so on. But maybe there's something I'm not seeing. So if that's it with the question, we can get on with the architecture.
Yeah, sure. Thanks for answering my question.
Awesome. I hope that was good enough. So here's the broad architecture. This is the most detail intensive slide here because we will step a little deeper into what's basically going on. So as we mentioned, there is a sort of federated setup here. There's a cluster of cluster sort of situation going on. You have your root orchestrator. And yes, I know you're thinking single point of failure, which is somewhat correct, but not quite, as we'll see later. You have what's called like the two major components of the service manager and the system manager. The system manager manages everything else. The service manager handles deciding where to put what service, right? And once you have your root orchestrator talking to a bunch of clusters, each cluster has their own cluster orchestrator. I hope my mouse pointer is visible. Is there a laser pointer I can use? Oh, never mind. Okay, do not want to do that. Seem to be running into something. Yeah. So for each cluster, you have your own local cluster orchestrator. And that cluster orchestrator talks to each and every worker node that you have. So right now, like if I basically remove the root orchestrator from the equation, right? This cluster orchestrator with its worker nodes is pretty similar to what a proper Kubernetes deployment looks like with a single control plane node. And I think that's the analogy that they're trying to draw, is that you can have a cluster, but you can also have a cluster of clusters doing this. The reason they're doing this is because it turns out that having this sort of delegation is a lot cheaper as you scale out with your number of nodes. But from an architecture point of view, what they've got going on is they've got a root orchestrator, they've got a cluster orchestrator, and they've got a worker node, as many as you want for each cluster. The cool thing about this is that the root orchestrator does not need to have a single master setup. Maybe I'm not too familiar with the terminology, so you'll have to help me out there. But seems correct. So apologies. So I think what's going on here is that the cool part here is that the root orchestrator need not know the minutiae of every single worker node status, right? What Orchestra lets you do is it lets you provide an SLA descriptor. So in Kubernetes, you have a manifest file that says, hey, I want this container. I want these many instances of this image. And I want, I want to have these network connections. I want to have this label. I want all of this stuff. And Kubernetes will take care of scheduling it for you. Maybe across different nodes itself, but Kubernetes takes care of doing the scheduling for you. When you give it a memory, CPU, bandwidth with a CNI plugin requirement and so on. But Orchestra basically lets you submit what's called what it calls an SLA descriptor. So as you can see, you can provide your memory requirement, CPUs, your GPU requirement, your latency requirement, which is something I haven't seen in Kubernetes or in any other scheduling system, area and location, as your system gets more geographically spread out. This is something that you can provide. Rigidness and convergence time are two very interesting factors mentioned later in the paper, and we'll get to them if we have time in the end. But what you should know is that this is how you submit your quote unquote manifest, right? You say, I want this much memory, CPU, GPU. I can also specify what area I want this to be present in and what latency I want my deployment to have, right? So once you submit this descriptor, the root orchestrator basically says, okay, I have this requirement. And then it selects clusters. It doesn't select worker nodes. So it ranks clusters. And in those clusters, it hands off scheduling authority to the clusters themselves. So then the clusters decide on which worker nodes to schedule what containers or what applications. And that's what the node engine does. So if you're familiar with Kubernetes, your node engine is in parallel to your kubelet. The execution runtime that they focus on is containerd, and the net manager is something like your container network interface that you have with Kubernetes. So I hope the architecture is somewhat clear. Please feel free to drop questions in the chat. And getting back to why this is a good idea, they ran an experiment basically, and they managed to show that as your number of nodes increases, the time it takes for your orchestrator to decide where to schedule what increases, right? Which makes sense. You have more factors to consider. I'm not exactly sure about the complexity of that increment or the complexity of that algorithm, but enough to make a difference is what I would say. So what they basically found out was that as in when you split your cluster into smaller clusters and try and balance it out, it takes you a lot less time to schedule it. Why this is the particular metric they chose to optimize is something that I don't quite know. And I also want to know how high availability Kubernetes with a distributed control plane setup deals with this. But those are questions I have. So because, distributing that scheduling problem, like running it on top of a distributed system, need not always mean it runs faster, right? In many cases, it can be quite the opposite, might run slower. So
a quick question here. One thing that I don't quite understand, and it just might be me. 45 root cluster to 1 ratio. What could you explain that a little?
I think what they did was on the leftmost side of the graph, you have one cluster with 45 workers. And on the rightmost side of the graph, you have 45 clusters with 1 worker each, right? And when you had to schedule across these clusters, they found out that obviously it takes a lot more time to coordinate between clusters, right? Because you also have much more stronger logical boundaries that you draw between clusters and between nodes. So between nodes, it's fairly, I won't say simple, but it is less complex because there is one central point of data collection for that, which is your orchestrator, right? But when you go across clusters, it becomes a lot more difficult because you have a lot more entities simply to keep track of. So I think what they're trying to highlight is that there is some sort of balance that you have, because when you do have multiple clusters present and they're somewhat balanced, right? Because I think they're talking about the optimum being 9 clusters with 5 workers each. That gives you the minimum scheduling time that you have, or the optimum scheduling time that you have. Forgive me, I'm not too sure what the exact terminology they use was. They do get the best result in terms of the least scheduling time in that case. So I hope that answers your question.
Yeah, in the interest of time, I wouldn't take up too much of your time here, but it's a little bit complicated for me because root can also mean a cluster, right? You can have a root cluster, a root cluster within Orchestra, and you can have clusters that are being managed by that root cluster.
Yeah, that is fair. I think we'll have to take some more time to, I have to take some more time to dive into this. I don't know if other folks here have understood this better.
What these graphs really show, right? So, for different cluster to worker ratios, right? So if you have, essentially, if you have more workers, you're going to spend more time scheduling at the cluster level, right? Because it's a hierarchical clustering. Your total scheduling time is composed of, how long does it take at the root level to, tell the cluster what to do, and then how long does it take for the cluster to actually find the workers, right?
Yeah,
so if you have more workers at the cluster, that's what the blue line represents. You're gonna the blue graph, blue line. You're gonna spend more time, at the second level in this 2-level hierarchy. You're gonna spend more time, searching your worker nodes at the cluster level. Now, if you have a lot of clusters, obviously, then you're gonna spend more time at the root level, right? So but I'm not sure, there is really like a balance that, exists. Like, usually you may not have this like ability to, separate, like, okay, I'm gonna have this many clusters, right? Their model is like, someone is providing the cluster, they subscribe. So you don't really control how many nodes you may have in the cluster, and those clusters subscribe to the root. So the root doesn't really have a control of how many clusters it has. So in my mind, this graph becomes kind of pointless, but yeah.
Yeah, I think they're trying to highlight the general utility of hierarchical clustering. And in that sense, I feel like it's a fair representation, because ideally what they're trying to show is that it takes a lot less compute at the root level, which they did manage to achieve with that. Because I believe the paper recommends at least that your root orchestrator be somewhere that's accessible by every single cluster orchestrator. So that's ideally somewhere in the cloud. So in that sense, I think they managed to, like, this graph does manage to show you that there is some level where you have a relative minimum of both less time taken to schedule within the cluster and less time taken to schedule at the root level as well. So in that sense, I think it makes sense. So any other questions? Do we move on? Awesome. So we've covered this. There's an SLA descriptor that you get. The root orchestrator basically need not know the state of the entire cluster at once. That's what the main advantage here is, right? So you provide this descriptor, the root orchestrator says, okay, cool, I have a bunch of clusters that I want to schedule over. I'm ranking them. I'm picking which clusters to schedule what over. And I'm letting the clusters decide which worker nodes to schedule which thing over. And it's not my headache anymore, which is basically the big win that the root orchestrator gets through here. Coming to my favorite part of this paper so far, almost all communication in this orchestrated setup happens via tunneling, right? So if I have, let's say, I have a service here on this ARM worker 1, and I have to have it talk to worker M here on cluster 2, that happens via tunneling. And to me, this is very interesting as a design choice, because I feel like you are sort of re-implementing another layer of routing on top of what already exists. But it is fair to some extent, because setting it up to go through your common internet is a problem. You have NAT traversals that you have to do. You have the ISPs come into the picture. It's very complicated. So to me, this was like a small point of contention where I was like, is this really the best way to go about this? And that is one of the questions I still have. So if there's someone who's probably a little more knowledgeable about this, I would love to learn some more about this. But the TLDR is like service to service communication happens through tunneling, and they use proxy tun to do this. They also have address conversion tables that allow you to do semantic routing. So through this, because everything is happening through tunneling, your nodes themselves have a large amount of control over how your connections get routed. So technically speaking, as a feature, if I wanted to, I could say, I want the closest video analytics service. And based on whatever metrics I have to define closeness, I can, maybe via latency, maybe in a geographical region, I can have my net manager, which handles all my network communication, give me the IP address for the closest service without me having to manually calculate it as a part of my application code. So this is something that I found really cool. They also let you do the same for round robin, for load balancing. The video of their presentation at the actual ATC has a small example of them doing this. And this is something that I personally found really cool. So any questions about this?
Yeah, this is another area where this idea of edge computing sort of complex for me. And where the entity, which is a customer, being some device like the EV, or I don't know, users within a particular proximity of this service, further becomes ambiguous, because in this case, a customer can then be another service, right? Which is kind of interesting, at least the way I'm understanding it is, okay, I want to deploy my thing, but I also want my thing to be close to another, as close to another service as possible. And Kubernetes does this already, sort of with, I forget the term, but there is a way to group containers onto a particular node where other containers exist, right?
I think you're looking for affinity.
Right. I think it's called node affinity, right? So it's like, okay, what is this trying to solve? Like, is it, scheduling services closer to other services? Or is that also a benefit that is realized in edge computing, which obviously I can see that being one. Anyway, sorry, my ramblings are probably more distracting than anything.
No, I think it adds some much needed context about the paper in general, because this is, to me, a very new domain. I have very little clue about what the state of the art in edge computing is, or edge routing for that matter is. So it does make sense. I found this entire thing somewhat peculiar until I realized that there's probably no better way to do it except for tunneling, because you can't really, as a part of your orchestrator, have negotiations with your ISP for a static IP and so on. So that seems a little infeasible to me. So I think this is probably the best way to do it. But what they're trying to get at is, hey, if you want to do this, you can, because the idea is that it's a heterogeneous setup, right? So I might have an NUC, I might have 4 Raspberry Pis in my smart farm or whatever, right? I can say that I want to deploy through a processor constraint. I can say I want my image recognition service to only be on the NUC, and I want everything else to be anywhere else. It's fine, right? So I think it's more about the fact that you can do this sort of thing instead of them having a clearly designed edge case for it. I think they're sort of hoping that this is already a realized edge case that they have. So any other questions on this? Being none, we shall go on. Yeah, again, the same question that we were asking, right? I also do understand that the internet itself is somewhat decentralized to the same extent, but I'm thinking more in the context of edge devices, right? So even for something like WebSockets, you have what's called or even for something like WebRTC, right, which is client-to-client, peer-to-peer. You do have a turn server that lets you connect to other clients by shipping manifests across, basically. And that solves the reachability problem, right? Even in Orchestra, you have your root orchestrator propagating some of your reachability information about how exactly to reach another node, what the route for that is. But there's a pretty complex section of the paper. So if you're more interested in that, I would strongly urge you to dive deeper into that section. Another interesting fact is that worker nodes connect with the cluster orchestrator via an MQTT broker. So they mentioned that they use Mosquito, which is an MQTT broker that is open source, if I'm not wrong. And this to me stood out as a very interesting choice, because I really haven't seen MQTT be a part of an orchestration system before. It can work, obviously, but should it be used in non-edge situations is my question. But this is something that just struck me as interesting, because I've never seen an orchestrator use MQTT as a part of the framework. And they also use MQTT topics in that sense to subscribe to change information coming from each of your worker nodes via the node manager. So an interesting tidbit there. They have a bunch of really cool scheduling algorithms here. Resource only match basically only cares about matching your processor, memory, and so on requirements, CPU and memory requirements. And latency and distance aware placement cares about your latency requirements and your distance awareness requirements. So I didn't dive too much into the math of this because I did not understand any of it. But they do seem to be talking about something called Vivaldi, which they've mentioned in the paper. I believe that is what they are using to get more context for their distance information. So if you're interested, please go ahead and check that out. And I think, yeah, so they also mentioned, as we come to the end of this presentation, I think I've overshot by a bit, so apologies for that. But as we come to the end of this presentation, right, they did mention that they're looking at demi-kernels for an orchestrator, which to me is very, very interesting, because having a demi-kernel that is built specifically to help with orchestration is a very interesting idea. I think there's already some variant of a Linux operating system that is somewhat oriented towards doing this. Like it ships with Kubernetes inbuilt. I forget the name, but I know there is something like this. It ships with Kubernetes inbuilt, so you can, basically just like set it up and instantly have it be a part of your cluster. I think that's sort of what they're going for, but it is a very interesting question to ponder on about what exactly a demi-kernel purpose built for the edge looks like, because you'll have a bunch of various hardware requirements to comply with, protocol requirements, and so very interesting stuff going on there. Another question I have is, why exactly did they use Python for the root orchestrator? Their networking components are written in Go, and they mentioned that that's because they want a low footprint. And I don't quite get why they use Python for the root orchestrator, but hey, that's probably just me. So yeah. Is tunneling necessary for reachability? I'm, again, not too personally sure about that. But getting to the interesting part, when they did their test evaluation, right, they mentioned that for Orchestra to be comparable with K8s, K3s, and micro-K8s, they ran Orchestra in single cluster mode, which basically means that they didn't have multiple clusters interacting with each other. I believe they only had one, which to me raises some serious questions about how exactly effective these benchmarks are, right? Because if you're not testing on the biggest buy of your framework, which is that, hey, I can do it across multiple clusters. I have, scheduler performance here being something that is important. How exactly, like for the majority of their tests, at least, I believe they ran Orchestra in single cluster mode. When they were benchmarking their schedulers, they simulated a bunch of clusters, if I'm not wrong, and they ran it there. But this is something to be very mindful about, because I felt like this was a little bit strange to me, at least from my experience, rather limited experience. But that is something that we can look a little bit more into. And I think that brings me to the end of my presentation. So thank you so much for listening to me. I hope this has been a valuable use of your time, and I hope everyone learned something from this. So thanks a lot. I shall stop sharing my screen.